Welcome everybody to the first in our SOLAS for Missing Data Analysis webinar series. There will be several this year, and this is the first of the new year. So thanks for logging in. My name is Andrew Granell. I'm a statistician here at Statistical Solutions. And my colleague Owen Murphy is here with me too. And just to set out the structure of this webinar, it's going to be roughly half an hour long. I'll be going through some slides here first, just to give you the basic background on the material and some theory on the model, and then I'll be showing you a practical example in SOLAS on how to do it. If it ever at all during the webinar you have a question for myself, just use the text box provided by the GoToMeeting, and just put your question there and submit your question, and my colleague Owen here will be handling all questions, and of course I'll be answering some questions as we go through as well. If we don't have enough time to answer everybody's question, everybody will be followed up with. If you have a question, you will definitely get an answer. And if you want to follow up after the webinar, you can always send me an email or anything. I have all the details at the end of the webinar. So also, if you need to zoom in or anything, if the screen is too small, just at the bottom right-hand corner of your GoToWebinar window, there's a little arrow, and if you click on that, you can zoom in or zoom out depending on the size of your screen. So we'll just get started. So just an outline of the presentation here. I'll just go through the missing data aspects, traditional methods of dealing with missing data, the missing data patterns, defining missingness. I'll go through the methods and theory of predictive model-based method that we're talking about today. I'll give a worked example and some post-imputation analysis. I'll have a quick break halfway through if anyone has any questions, and we'll be taking questions at the very end as well. So as I said again, if you have a question, just put it through the question box there, or the chat box, and Owen will be dealing with those. So firstly, traditionally, how was missing data being dealt with? Well, many people obviously have heard of complete case analysis, where if any case in your data set has a missing value, that is just automatically deleted, and you just deal with the people or the cases or patients or whatever who have a full set of answers or responses. Now, we feel this can lead to biasing in your analysis or your inference of the output, because there may be bias in the people or the cases that you've deleted. There may be a reason why there is missing data there, and you just be deleting it for no apparent reason. Another method was complete case analysis, where you'd select out the variables that you want to run your analysis on or run your model on, and you just use that data. The pitfalls with that is that you're not comparing like with like, or using different sample sizes, etc., and it gets quite messy. Another method that I just want to touch on is single imputation. That's quite commonly used. Methods like group means, where you're just imputing the mean of the variable, or hot decking, or last observation carry forward, where that's most commonly found in longitudinal studies, where you impute the if a value is recorded at one time period and is missing for the next time period, you just impute the last observation that is made. So there are some traditional methods that are used, and we feel that multi-imputation is a much stronger method of dealing with missing data, and we'll go through that now shortly. So the first thing you have to do when looking at missing data is you have to observe the pattern of missing data in your data set or your database. There are two distinct types of patterns: a monotone pattern and a non-monotone pattern. The monotone pattern is defined that in a way is that variables in the data set or database can be arranged such that your y at j plus 1 are missing for all cases where Y and J are missing. So almost the missingness is contained with one observation is also contained in another observation, the following or preceding observation. As I mentioned before, this is commonly found in longitudinal data as well, where again a case or patient, for example, have showed up at one time period and hasn't shown up for the remaining time periods, and therefore subsequent missing data. A non-monotone pattern is the opposite, where this corresponds to the arbitrary missing data where covariates and cases cannot be rearranged to produce any sort of pattern. And this is important when you're going to when you're looking at the order in which you need to impute data. It's important to take this into account, and again I'll explain this in a minute. So once you've looked at the data pattern, the missing data pattern in your data, you have to go about defining what type of missingness there is and what type of missingness exists. There are three main types of missingness: missing completely at random, missing at random, and missing not at random. Missing completely at random, this corresponds to the data that is missing does not depend on the observed or unobserved data in the study. So nothing that you have recorded in the study or not recorded can explain or is dependent on the missing data. So if we define our outcome variable as y, a missingness indicator as m, and the covariates by x, we can say that for missing completely at random, the probability of missingness given the observed values and the unobserved values for the covariates and the observed and unobserved values for the outcome variable, this is equal to just the probability of missingness, so it's completely independent. Missing at random then, this corresponds to the data that is missing does not depend on the unobserved data in the study. So it doesn't depend on the missing data, but it may depend on something else in the study. So again, using the same notation, the probability of missingness given the observed and unobserved covariates and the observed and unobserved values for the outcome variable is equal to the probability of missingness given the observed values for the covariates and the observed values for the outcome variable. And again, if we break it down for looking at a monotone pattern, where we have here yj plus denotes the history of measurements, denotes the future measurements, yj minus denotes the history, so the previous measurements. The mj is the indicator for missingness, so it's equal to 0 means missing, and m equal to 1 means observed. Then the probability of yj plus given yj minus x and m equal to 1 is equal to the probability of yj plus given yj minus x and m equal to 0. So the probability of being observed is equal to the probability of being missing. And finally, missing not at random or not missing at random. This corresponds to the data that is missing in your data set depends on the unobserved data itself. So the probability of using the same notation as before for monotone pattern, the probability of yj plus given z, which is this fully observed data, denotes fully observed data, given z minus x and m equal to 1 is not equal to the probability of yj plus given z, x, and m equal to 0. So now that we've defined our missing data pattern and our missingness, we can now go ahead and look at our actual model. And this is one of many multiple imputation models, and this is called the predictive model-based method. So as you can guess, it incorporates a predictive model of some sort. And at the top level of this model, you have to look at what kind of variables you're dealing with, and you have to look at what approach you're going to take. So there's two separate approaches in this model, depending on what definition of variable you have. If you have a continuous variable or an ordinal variable, you have to use a ordinary least squares regression model. And if you have a nominal variable or a categorical variable, then this discriminant multiple imputation model is applied. And I'll just run through those quickly now. So firstly, with the ordinary least squares regression model, the model is estimated firstly on the observed data. So using this model, regression parameters are randomly drawn from their Bayesian posterior distribution to generate values to be imputed. And this includes a random deviation to ensure extra uncertainty about the unknown true model. A linear regression model regresses the observed outcome variable onto the observed covariates to obtain a prediction equation in the form of, as everybody can recognize, the missing component of the outcome variable equals some intercept plus beta times the missing component of the covariates. The parameter values from the regression model are drawn from the posterior distribution given the observed data using non-informative priors. So when applying this ordinary least squares model as well, we also have to take two separate approaches, one for completely observed, because some variables in your data set may be completely observed and some may be incompletely observed. So there's two separate models run. So this multiple regression model here, for the completely observed model, has your intercept, your beta 1, x1, and so on for as many variables as you have in the data. And for the incompletely observed covariates, we have to introduce this indicator variable or, which defines whether it's a complete or incomplete data set or variable, sorry. And we have the intercept beta 0 times beta 0, 1, 1 minus R1, and so on for the amount of variables that you have. And then you include the beta 1, R1, x1 down as far as, again, xp. So when we're dealing with categorical variables, then you have to take another approach called this discriminant imputation method, and this method is based on imputing, as I said, binary or categorical variables. And similarly, this is uses Bayes' theorem, and using Bayes' theorem, the probability that the missing value in the imputation variable is equal its corresponding category, given the set of observed values of the covariates and of the imputation variable. The model for the discriminant imputation is given by this equation here. The probability of the outcome variable equal to j given x, and this is where the phi function denotes the multivariate normal distribution, and pi denotes the a priori probability that the outcome variable is equal to its corresponding category. So this is for categorical and nominal data only. So what we're going to do now is we're going to put this model into practice. Again, if you have any questions at all, just fire them in through the text box there, and myself and Owen will get to them. I might just take a minute to see if any questions are coming in and if we can address any there. Okay, so guys, there was a few questions came flooding in there, so I'll just address the first few that came in, and we'll be getting back to everybody, absolutely. One interesting question there was what type of missingness is required for the multiple imputations methods, and you can impute um, missing data when it falls under, primarily when it falls under missing at random, but also you can impute missing completely at random too. You cannot impute data that is defined as not missing at random. This is non-ignorable missing data, and you can't impute this data. It's not recommended you impute not missing at random data. But under the other two circumstances, excuse me, missing at random and missing completely at random, you can impute that type of data. Another question was, is M binary? Yes, the M component I was talking about earlier is a 1 or a 0 just to indicate whether a value is missing or not. And somebody asked, what is the OR value in the ordinary least squares method? The OR value, again, is similar to M. It's a binary value that differentiates whether a case is, or a variable has a missing value or not. So I'll just move on to this SOLAS example and just show you a quick example in SOLAS. So I'll open up SOLAS there now. So when you open up SOLAS here, this is the window you get, and you have a file. You can open a new data set and fill in and enter in data by hand, or you can open a data set. Formats that are provided for in SOLAS are Excel, CSV, .text, and .dat. So flat file format and Excel file format. We have the script language window where you can enter the SOLAS code and enter it here, and out comes the log and the output. This is quite handy. I'll show you the script feature. There's a 250-page manual on the script language. It's quite easy to pick up if you use any of the other major statistical analysis packages. This is quite easy language to pick up. And what the nice feature about SOLAS is that it's mainly click and drag technology, but once you run an imputation or once you run a analysis, it also generates the code for you, so you can alter. You don't have to type the code from scratch. You can alter the code that's created by the analysis you want to do. Also, there's the system preferences. Before you even get started, you can set up what you like, the way you want your plots to appear, what descriptive statistics do you want to come out, what preferences you like for the imputation models, the regression, what diagnostic tests you like to do, and it does it all automatically from there on in. So you can define it here before you even get started. You can define everything, and it'll from then on out it'll define it in that way. And we also have the help index here. So I'm going to open up a data set, predictive model based demo. And this is quite a small data set because I don't want to be wasting time waiting for the imputations to be created. So I just picked a small data set just for demo purposes only. But this can handle quite large data sets, and it has been tested on those too. So as I spoke earlier in my presentation slides, the first thing you kind of want to look at is your missing data pattern. And so we have this table that you can do. You just click View Missing Data Pattern, and you can either select by clicking and dragging, select your variables, or you can just click Use All. So here we have a table of the missing data where blue denotes missing and white denotes observed. So here we have 11 variables and 50 cases. But if you had thousands of cases, you don't want to be scrolling down to see all the missing data and its patterns. So we have this nice collapse feature, which essentially, instead of having one row for each case, it collapsed it all out. So now we know that we have 39 completely observed cases. We have one case with a missing value for variable 9, and etc. Now also we can split this into monotone, non-monotone pattern. So now here we have the red as the monotone pattern, and green here is the non-monotone pattern. So as I described earlier, the monotone pattern looks like it occurs when the variables can be ordered from left to right here, such that a variable in the left is at least observed as all variables from the right. So if A is fully observed and B is sometimes missing, A and B form a monotone pattern. So that's the missing data pattern stuff. We're assuming here that the type of missingness is missing at random. We also have this margin plot feature here, where it's like a scatter plot. So you have your scatter plot layout here, but in the margin we have these box plots. And the blue box plot gives the distribution of the observed data, the blue dots, and the red box plot shows the distribution of the missing data, which is the data points are given here in the margin as well for the missing data. So these data points down here on the x-axis represent a observed value for cholesterol 1 and a corresponding missing value for cholesterol 3. So this is quite a neat feature, because you can see the distribution of the missingness for a relationship between two variables. So this study is a medical study, and essentially it was recorded the patient's age, the symptom duration, their BMI level at baseline value, 1 month after, 2 months after, and 3 months after, and then the cholesterol value at baseline and cholesterol at 1 month after, 2 months after, and 3 months after baseline. So symptom duration and age, baseline value for BMI and baseline value for cholesterol, these 4 variables are completely observed, and then the 3 months after for each BMI and cholesterol, these 6 variables are incompletely observed. So what we want to do is impute these ones using the other covariates as characteristic builders. So I'm going to run an imputation here. We're going to run the predictive model-based method. So you just go analysis, multiple imputation, and select your method. We also have features for transforming variables, defining your variable, setting your variable attributes. Are they nominal, ordinal, continuous, etc. Also, you can highlight without having to select the variable columns or rows. You can automatically define how you want to select the data. Different plotting, margin plot, or scatter plots, box plots, histograms, etc. Various features here. So also we have pre and post imputation analysis. You can do descriptive statistics, regression, ANOVAs, t-tables, etc. like that. So I'm going to run a multiple imputation using the predictive model base method. And as I said, I'm going to use the completely observed variables. So that's symptom duration, age, baseline BMI, and baseline cholesterol levels. I'm going to use these as what I call the fixed covariates. So these are going to set up the characteristics. So I'm going to be comparing people with similar ages, similar symptom durations, and similar baseline BMI and cholesterol levels. And I'm going to use these comparisons to impute similar values based on the regression model for the missing, the incomplete variables. Here you can define how many imputations you want to do. The default is 5. The maximum in SOLAS is 50. But I'm just going to do 5 here, because it'll become apparent why I'm doing 5 in a minute, just to show you quickly the post-imputation analysis too. You can define your non-monotone and monotone patterns here too by just selecting for BMI1 here. You can select which variables should be monotone, non-monotone. And then the advanced options, you can set a seed, and this is very important for example, if you want to run your analysis again the exact same way as you did before, because there's a random element included in this. So the random seed here lets you regenerate an analysis the same way as you would have done before, and you have to save this random seed so you can redo analysis. You can change the seed if you want to do the same analysis again and get a slightly different answer. So I'm going to run this. So it's going to chug out my 5 data sets. So I said 5 imputations. So the red values are the monotone values that have been imputed, and the green values here are the non-monotone values that have been imputed. And down the bottom here I have a tab, so I have my 5 data sets with 5 imputations. So now I have 5 values for each missing value. So it's always good to do a complete case analysis and then compare it to your multiple imputation analysis and see if there's any difference. So I'm going to run a multiple regression analysis here, and I'm going to use the cholesterol value for the second month after baseline as my outcome variable. So now we're printed out a window here with 2 internal windows, and essentially this is like a stepwise regression. So the first window is variables in the model, and the second window is variables not in the model. And essentially you can just click and drag variables into the model, and like stepwise fashion. And here we have the multiple R square, or the multiple R value, R squared value, etc., and also the equation for the multiple regression. We have many options here to do diagnostics and inference. We can do diagnostic plots. We can also see different covariance matrices and so on. And also we can just do, instead of clicking and dragging, we can do automatic stepping. So I can tell SOLAS to do the stepping for me, which I'm going to do right now. So you can set the tolerance and various values. When you click OK, it'll pop the first variable in. So it said cholesterol 1 month after baseline is the most significant value. Let's see if anything else is. Cholesterol 3 months after baseline is also significant. Is there anything else? No. So in my complete case analysis, so before I did imputation, when I'm doing a multiple regression for cholesterol 2, cholesterol 3, and cholesterol 1 are significant variables for the model. Now I'm going to do the exact same analysis on my imputed data set, and I can do the same analysis for all 5 data sets. So I'm going to go Analyze, Regression, Multiple Regression. I'm going to pick cholesterol 2 as my outcome variable. And again, now I'm given the same window with the 2 internal windows, but the slight difference is now I've got 5 pages, 1 for each data set. So I'm doing this analysis, but now I'm doing it 1 for each data set for my imputed. I'm going to do the automatic stepping again to let SOLAS do the decision making for me, but you can do it manually if you need to force a variable in. So again here, no real change for data set 1, cholesterol 1 and 3 again. What's it like for data set 2? So data set 2, it's telling me that BMI 3 is also a significant variable. What about data set 3? Data set 3 says just cholesterol 1 and 3. Data set 4 includes BMI 3. Data set 5 so data set 5 also has BMI 3 is included in there. So let's go back to data set 1 and 3. So data set 1, BMI, the p-value for BMI 3 is quite close to 0.05, and data set 3 also similarly, the BMI value is quite close to 0.05. So it's close to being significant. So what I'm going to do is I'm going to force it into the model. And as you can see here, we've got quite a strong relationship, 86% R squared. So, and this will replicate for each page. So again, quite a high R squared in the relationship. And at the very end here, you might notice we have a combine tab, and this will give us the output for the combined analysis. So what I mean by that is It'll give us the multiple correlation across all 5 data sets, 93.6%. And then it'll give us the mean value for each coefficient across the 5 data sets, and the standard error associated with that value. And then it'll also give us the partial correlations of the variables not in the model. So this combine tab here is very handy because it tells you the correlation between each data set and also gives you the mean model coefficient and standard error associated with that coefficient, so you can see how accurate the value for the coefficient is. So just comparing this back to the complete case analysis. In the complete case analysis, we said cholesterol 1 and 3 are the significant values. After imputation, BMI 3 has now become significant too, which is something we might have missed out on in our initial analysis. So not to run over time here or anything, that's kind of the last note I wanted to finish on, was just to say that you could all overlook something without using multiple imputation, or something can be discovered when you use multiple imputation in your post-imputation analysis. I would also advise to do more than just 5 imputations, because the more imputations you do, the greater spread and the distribution of each imputed value you can make it out better. So more than 20 is kind of the industry standard now. So that's about it. That brings us to the end of the webinar. I hope it was okay for you and that you enjoyed it. I certainly did, and we'll be taking any questions you want to bring in. Again, just pop the questions through. I'll take a few minutes now to answer a couple of questions, and just pop them through the text box. And thanks again for attending, and we can address any questions you have there now. So I'll take a minute to read a few questions, and we'll have a bit of discussion here.